This week we have Johan Martens. We'll be talking about equivariance and what it was.
Thank you, and thanks for the chance to speak here. So I'll be talking about some joint work, some old work with Michael present here that I'll just mention, but that somehow is a starting point. And then various stages of more recent work with Hilgert and Manon, Dancer and Kerwin, and then some ongoing joint work with Dancer, Grimminger, and Zhang. Maybe I should begin by making a bit of a statement. Some people say that in life, you can only be a good citizen of the world if you are first a good provincial somewhere. I don't know if this is true, but I thought of sort of taking that a bit as a slogan for this talk to begin by being a provincial in sort of the neck of the woods where I tend to hang out and then see if we can be a citizen of the world at the end. But then predictably, I started writing out my talk and it became longer and longer. So I can't make any promises on being a citizen of the world. We might just have to stay with my provincialism. So I want to talk about a certain pattern that you have in equivariant geometry. And I'm going to be talking about three flavors of geometry. I'll abbreviate algebraic geometry by C. Then real symplectic geometry by little omega and capital omega for the complex symplectic geometry. I might slip into referring to this as hyperkahler geometry, even though I will have very little things to say that are fully understood on the metric side. And so in each of these geometries, I want to think about an equivariant setting. So I'll have a group K or its complexification that acts on some space that I'll denote by X. So that's either an algebraic variety, in which you have a linearized group action, or real symplectic manifold or a complex symplectic manifold. And well, very important is that in each of these three contexts, you have an associated reduction theory that I'll say something about. So GIT, symplectic reduction, and hyperkahler quotients or holomorphic symplectic quotients. And so what is the pattern that I want to think about? I want to start from so there's these operations in equivariant geometry that start from a space that is either the compact group or its complexification that acts on some space X. And out of that data, you get a new space. Just in the beginning, I'll try to indicate the general pattern. So I'll use a little bit of a clumsy notation, a modified space that I create out of this data. And it has to be this, we want this operation to be sufficiently functorial in the sense that it commutes with reduction, with the three reduction theories in a suitable sense. So if I have two commuting actions, let's say K1 times K2, or their complexifications that act on a space X, then typically if I modify by using one of the two actions, the other action descends. And so I can then choose in which order I apply this. And I want these two actions to commute. So what I really want is that if I take X and I do my K1 modification, and then I reduce by K2, that should be the same as when I first reduce by K2, and then I apply my K1 modification. Sorry, K1 modification. So this is the pattern of operation that I want to think about, and I want to give 5 examples of these, of which I'll focus on the last 2, which are going to be the contraction and the implosion operation. Now, why is this such a convenient property to have? Well, it makes life simpler in the following sense. You can invoke a very cheap trick that says that in each of these contexts, the variety itself is, or the space itself is isomorphic, canonically isomorphic, and G equivariantly isomorphic, as the reduction of the space times a standard space that is either the cotangent bundle of the compact group in the case of real symplectic geometry, or the reductive group in the algebraic setting, or the cotangent bundle, the complex cotangent bundle to the reductive group by G or KC. So I'm again, for now, I'm going to be very sloppy. The 2 bars just refer to the reduction in either of the 3 categories, even though at some point later I'll have to be a bit more precise about this. So this is a very cheap statement, but as a corollary of this, it essentially tells you, if you have this functorial property, it tells you that your operation is entirely determined by what happens on these spaces. So your modification is going to be the same as taking the reduction of your original space with the modification of whatever space you have to plug in here. Take this product and you reduce this. So what this tells you is that you really have to understand what is happening just for these spaces, and that is enough to see what is happening in general. So here we have a modification, and here I also have a modification. No, not yet. Modification. So modifications for me is now something abstract, and I'm going to give 5 examples of what the modification is, or can be, in order to fill in what this pattern is. So this is the crucial property that allows us to say that the universal modification is just a modification applied to these things. And this is where, so of course, there's going to be links between these theories. You go back and forth between an algebraic geometric picture and a real symplectic picture by choosing a suitable Kahler structure. And the complex symplectic version is going to be inspired by both, take sort of ingredients, both of the real symplectic and the complex algebraic version. But this theorem, strictly, importantly, this theorem here does not hold in Kahler geometry or in hyperkahler geometry. So there are still things that you can say in the presence of a metric, but this theorem essentially fails. For instance, in the case when you look at hyperkahler metrics on the cotangent bundle of G, as far as I know, there's only one way to construct these, due to work by Cronheimer, which tells you that this space does possess hyperkahler metrics determined as a solution of NAM equations on an interval, but the length of the interval is a parameter. And so if this were to hold, then if you take the reduction by 2 copies of that space, you would have to get the same thing. But what happens is, if you have 2 copies, you need to assign a parameter to each of them. And when you take the reduction, you get the space whose parameter is the sum of the two lengths. You take two intervals, norm equation of them, fuse them together, but the lengths add. And that's actually similar stories. There's more ways of getting Kahler structures here, but at least one of them is through something known as the baby norm equations, where the exact same thing holds. Okay, so this is all still very abstract. So maybe I should start giving some examples. So that's what I'm going to be doing for most of today. Now, the first example, in some sense, is the most trivial one, but it's worth mentioning. So the first operation or modification that you can do is reduction itself. So reduction itself, if you have two commuting group actions, then reducing by the order in which you reduce doesn't matter. So that actually falls into the pattern. Now, what happens then by this sort of philosophy? You have to look at the reduction of the group itself. So what happens there? On the complex side, essentially life is a little bit boring, because what you get there is just, so this is of course just GIT, and the universal operation, take the quotient of the group by itself, is just a point. So that's a little bit boring. But on surprise, or maybe slightly surprisingly, on the symplectic reduction side, that's what's happening here. You can actually stretch that a little bit, because the Marsden-Weinstein theorem, where you take a level set of the moment map and typically maybe a level set at 0 and quotient out by the group, that actually holds in slightly greater generality. You don't just have to take the level set of a point in the dual of the center. You can actually take an arbitrary coadjoint orbit. And when you do that here, you get coadjoint orbits, or in algebraic geometry, you get flag varieties. So what we see as the universal version of symplectic reduction are flag varieties. I'll write it in the algebraic geometric sense. That's what we have, coadjoint orbits for a compact group. And then on the holomorphic symplectic side, you could do the same thing. The symplectic reduction, essentially, that's just a complex version of the Marsden-Weinstein theorem. But if you want to stay within a nice category, say varieties maybe that are projective over an affine, you probably want to take a closure there. And so what you end up then is what is known as a constant variety, which is the closure of a complex coadjoint orbit. So that's the first example. Not particularly interesting, but it falls within this pattern. Okay. So let's then go to a slightly more interesting case of something that falls within this pattern. And that is, let's begin by doing abelian symplectic cutting. And so again, you have three flavors of this. You have the complex one, and then you have the real symplectic one, which was the original one. So maybe I should put some names to this. This was due to Lerman. And I'll explain very briefly what this is. So the real symplectic version says, so now we have our compact torus that acts on a symplectic variety X in an Hamiltonian way, and we have a polytope inside of the dual of the Lie algebra, and the cut space then, out of this data, we create a cut space, which I'll denote by X with a lower p, is nothing but the preimage of the moment map of this polytope. So we have some polytope. Actually, could be a polyhedral set, doesn't have to be finite. And it's going to have normal vectors to its faces. Each of these normal vectors is an element in T, so that actually gives us it's in the natural lattice of the Lie algebra. So that is going to give us a map of a circle into our torus. And what you need to do is you take the pre-image of this polytope under the moment map, and then you have to collapse exactly these on the pre-images of the faces. You collapse the associated circles. So you collapse the circle actions. On the faces.
Sorry, U is the moment map.
Yeah.
So the image of X is P.
No, the image of X is whatever it is. The image of X is going to be some subset in P. P is another polytope. So you're intersecting your moment polytope with this other polytope. And what you get is a new polytope. You're chopping it up, you're refining it. But it's very interesting to look at the universal case, because the universal case is now obtained by applying it to the cotangent bundle to the compact torus itself, whose moment map is surjective. So if you apply it to the universal one, you get a variety whose moment polytope now is P on the nose, and that is just the associated toric manifold. So here we get the universal version is the Hamiltonian toric manifold. So this is sort of the point of view that like to, in fact, in the first week we had a workshop here, and Ali Cross spoke about the Cox construction. So one of my pet peeves is that there's a better way of doing the Cox construction or the Delzant construction in symplectic geometry, which is rather than taking a reduction of an affine space, you should do a symplectic cut of the cotangent bundle, which does everything that the Delzant or Cox construction does, but it actually also works in greater generality. And so that's what we're doing here. We're creating the toric manifolds as symplectic cuts of the cotangent bundle. Yeah. Oh, so this is sorry, F are the faces. So for any face of my polytope, I get an associated circle or a map from the circle to the torus, and I just collapse that orbit on the pre-image of that face. Yeah, so my polytope lives in the dual of the Lie algebra. I want it to be a nice polytope, and in particular, this means that inside of my Lie algebra, I'm going to get a natural lattice. So all of these normal vectors are going to be lattice vectors, and that means that for each of these, I get a map from U1. It's a co-weight if you want. So for every phase, I have a circle attached, and I just collapse these circles on the preimage of them. So there's also an algebraic and a scalar version of this cutting, and so here you get historic varieties. So the names attached, this is maybe a little bit less foundational. Edidin and Graham, I think, did the algebraic cuts, and Burns, Gilliman, and Lerman did the scalar cuts. And then when you look at the hyperkahler version, the holomorphic symplectic version, this procedure now needs, rather than taking a polytope, it needs a hyperplane arrangement. And so this was introduced by Dancer and Swan. So what you do now is, so this is what is known as the hyperkahler modification. And what you end up with are, of course, the hypertoric varieties. So they essentially have this procedure where if you have a holomorphic symplectic action and you take a hyperplane inside the dual of the complex Lie algebra, now the Lie algebra of the complex torus, there's an operation that they call hyperkahler modification. And in particular, when you apply that to the cotangent bundle of the complex torus, you recover the hypertoric variety. So the hypertoric varieties are the universal hyperkahler modifications. Okay. And of course, people not familiar with this example. So examples of this operation in action are equivariant blowups. So for instance, if we start from affine space, the original moment map image was the first quadrant. And now, for instance, we can apply a polytope that is missing this vertex. And so in that case, you go to something like this, which is just the affine space blown up at the origin. But you can also take a polytope that maybe is missing everything beyond a certain distance. So you might also go to projective space. So you might think of CPN as the cut of C to the N for a suitable polytope. So those are just examples of this procedure. So yeah. So algebraically, so in both of these cases, there is this sort of tension between the way that you think about it. Symplectically, you are both, when you blow up and when you go to projective space, you're making the space smaller in that the volume goes down. Whereas in algebraic geometry, you actually think of it as making the space larger. The blow up, you take a point and replace it by a projective space, and the complexification is done by sticking a projective space in there. And that is related to the fact that this whole picture doesn't quite work on Kähler geometry. You sort of have to pick the way that you look at it. You can't have your cake and eat it too. You have to be a little bit selective. But it works on either case, on either side, but not simultaneously. So this is the abelian version of symplectic cutting. There's also a non-abelian version. But there, the hyper version is still completely missing. So maybe I'll just say something briefly. So in the real symplectic case, this was developed by Woodward and Meinrenken separately. And so what you have to do now is you look at your space X, which has a moment map into the dual of the Lie algebra now, which is non-abelian, but then you quotient this further, you collapse the coadjoint action further, and that gives you a map to the positive Weil chamber in the dual. So I'll call this map phi. And so the data that you need in the non-abelian case is you need a polytope, P, that is contained inside of this Wild chamber. But it has some, now we have to be a little bit careful about what happens when you're looking at the walls of this wild chamber. So if P meets phi of k, and phi of k is always going phi of x. Phi of x is what is known as the Kerwan polytope. So it's a polytope in this wild chamber. And so what Francis proved 30 years ago was that you also have convexity for this map in the non-abelian case. But if this meets, if the polytope that you choose meets this place in a wall of the wild chamber, or so if a face of P meets the Kerwan polytope in a wall of the wild chamber, it must do so perpendicularly. So that is the recipe, but then otherwise, you have a very similar story that now you take the preimage of your polytope under this map, under the map to that positive wild chamber, and you collapse the exact same story. And that, in order to have the consistency, this is what you must do there. Okay. So it's the exact same story as what we have here. So you take the faces of the polytope, and for these faces you get a circle, and you just collapse these circle orbits on the preimages of the corresponding faces. And in order to do that consistently, you need to have this perpendicular condition. And so where we came in, so this was joint work with Michael 10 years ago or so, is that under some mild condition, there is actually an algebraic version of this. So the condition is that now you can't just pick any polytope that satisfies this property. You need to choose a polytope whose outward normal vectors, outward normals to the faces of P have to be contained in the wild chamber itself. So something like this would not be good. This would be a polytope that doesn't satisfy this because these outward normals are just a bit too much all over the place. So this is not good, but you could do things like this. This is fine. So there's a mild condition. And if you do that, there's an algebraic version of this that uses the Edinburgh monoids, which I'll need later and I'll define later on.
So it's really with P that are not themselves faces of P plus, right?
Yes. So when I say a polytope here, I never, yeah, the faces of T plus do not count. Yeah. Yeah.
So in this Toria case, XP, I mean, is this somehow related to your earlier story? Is this a symplectic quotient of X times some other?
Yes. So what I wrote down here is essentially sort of a local surgery procedure. But so this is an aspect that I didn't mention. You can also think of it, there's a way of writing it as a global symplectic reduction, like so, where n is the number of faces of P. So there is a global, at the end of the day, typically all of these procedures, or many of these procedures are, can also be understood as some kind of a symplectic reduction. And so this is the one that you have here for the symplectic cutting.
And the start is that if you took X to be like I mean, this is supposed to be just a generalization of the construction of toric varieties as GX equations.
Yes, but this actually works more generally. So yeah, but yeah. And so what I said here, it's not just set theoretically on the interior of the polytope. You actually have a symplectomorphism, and so that's what Lerman showed. You can understand this way. And so the non-abelian version of this also goes through. And so when you think about the universal versions here, what you get now are the toroidal compactifications, the algebraic sides of the group G itself. For instance, the wonderful compactification is an example of the universal operation applied to itself. And then, as I said, on the holomorphic symplectic side, this is still completely open. And in fact, you could generalize this even. These toroidal compactifications of G for non-abelian G are examples of spherical varieties. And quite recently now, the hyperkahler version of spherical varieties has become sort of a mathematical object of interest, in particular through this big manuscript of Benfi, Sakellaridis, and Venkatesh that is phrased within geometric Langlands and number theoretic Langlands. A key ingredient of them is the notion of hyperspherical varieties. And for spherical varieties, we have a very nice combinatorial classification, but the hyper version of that is completely open. So on the abelian side, we do know how to classify hypertoric varieties, but hyperspherical varieties, we don't know how to classify them yet. So I think that's definitely a very interesting question. Okay, so these were sort of our warm-up examples of the pattern. So now I would like to get to ones that I would really like to discuss, which is implosion, and then in particular contraction. So implosion has been around, in particular on the symplectic side, for about 20 years, but the complex side is much more recent. So on the real symplectic side, this was due to Guillemin, Jeffrey, and Shamar. And what this looks like, so if I have a symplectic, real symplectic variety, then the imploded version of this is obtained by taking the pre-image now under the moment map of this dual of the Weil chamber. And so here it's maybe slightly confusing. I had this Weil chamber that was showing up here, where I had a map from the whole of the non-abelian, the dual of the non-abelian Lie algebra. That's where we collapse the coadjoint action. Here this shows up, but in a slightly different form. So here I'm thinking actually of this space as well. This is a subset of the dual of the Lie algebra, but using the weight decomposition, this actually canonically sits inside of K. So I can think of that as a subset, and I take the pre-image under the moment map now of this subset. So this is really going to drop my dimension. And again, I have to impose a certain equivalence relation. Maybe I want to indicate that is different from this one. So what happens is that essentially I want to collapse by the commutator subgroup of the stabilizer under the moment map. So what that means is here that 2 points x and y, I have to declare them equivalent if they have the same moment map and they lie in the same orbit for the commutator of the stabilizer of this group. Of this point, rather. So the generic point in the in this wild chamber, there I'm going to have the generic point is going to be regular, so this guy is going to be trivial. So generically on the interior of this wild chamber that I take, I do nothing, but on the walls I have to collapse something. And so this has some nice properties that were the main motivation, which was that if I take my implosion, so the implosion, if I start from a space with a k action, now the implosion is just going to have an action of the maximal torus of my group, but the reduction is the same. So this space already goes down in dimension from my original one, but when I take my original reduction by k, that is the same as taking the implosion and then reducing it by p. So if you're interested in some space where you need to reduce by a non-abelian action, this allows you to sidestep, switch to another space, which typically has to be stratified, but at that point you can just afford the luxury to just reduce to by a compact, by an abelian group, and that can be useful. So that is the story of the symplectic implosion. Now on the complex side, this can be understood, and this was mainly due to Francis. This can be understood as non-reductive GIT in the most simple case. So so we have here non-reductive GIT by where U is a unipotent radical, a maximal unipotent group inside of G. So it's an example of non-reductive GIT, but it's in the most benign case where the unipotent radical is actually sitting inside of a bigger group, and that bigger group acts. So a reductive group, exactly. And so you can now again ask, what is this universal version? So you have here your universal version of the cotangent bundle, and that is much more known on the algebraic side, because that is nothing but what you could call the affinization of G mod U, which people in geometric representation theory refer to as the base affine space. So what this space is nothing but spec of Kg of the U invariant ring of Kg, and so this is finitely generated. So it's still quite benign, and this space contains G mod U. It's strictly larger than G mod U.
So why should I think that this unipotent group is going into the story? Like from the symplectic side, I don't really see why I would expect some.
Yeah, it's a good question. So it's a very explicit hands-on identification between these two. So what you essentially do is you look at your dominant weights here, and you choose a bunch of generators of them as a semigroup. For each of these, you write down the associated irreducible representation that has that guy as its highest weight, and then each of these representations you pick a maximal a highest weight vector. And what you then do is that inside of that sum of these irreducible representations, there's a natural toric variety that sits there that is just obtained by moving these highest weight vectors around by a U1 and closing that off. So you get a natural toric a variety in there, and the entire closure of the G orbit is just moving that around by the compact group. And so what you essentially do is you find the same toric variety inside of here. So it's a toric variety whose moment map is the wild chamber. So in the fan picture, what you have is the wide cone, which is the cone generated by the simple roots. So you have that affine toric variety that you stick inside here, and then you find that when you move it around, it has exactly the same stabilizer. So it's a very hands-on construction that identifies these two. And so the U is sort of there because that is the part that kills off the highest. When you take the Lie algebra of that guy, that kills off these highest weight vectors. So that's how you match it. So it's a very hands-on description. You can, I mean, the most basic argument to say that this is plausible is just to look at dimensions. And from this recipe, you can quite easily see that the dimensions. So that is the standard story. But now things start to become a bit more recent when we look at the complex symplectic picture. And so now we are looking at complex symplectic implosion. Maybe I should actually take a board for this. And so that was done much more recently. So the key part to the algebraic picture is the fact that this invariant ring is finitely generated. Now, what you want to do on the complex side, and I'll just focus on what is happening on the universal side, is that you want to take the complex symplectic reduction of complex implosion. So now you want to take hyperkahler reduction of T star G by U. And so now I'll be precise and put 3 bars to say that I want to take here a hyperkahler quotient or more specifically a complex symplectic quotient. And another way of saying that is, so what you do when you take a holomorphic symplectic reduction is you take the level set of the moment map again, and then you take the group quotient, which you have to interpret here in the non-reductive GIT sense. Taking the level set of the moment map is not going to be a problem at all. We can write T star G as G times the Lie algebra. And so the moment map for U is just going to be you just take the product with the annihilator of the Lie algebra of that maximal unipotent group. That's not a problem at all. But then you have to take non-reductive GIT. So the question is really, when you just consider this variety here, is the U invariant part of its ring of regular functions finitely generated? And the answer is yes, but it's a much more subtle business. So this was done by Dancer, Kerwan, and Swan in type A. And then by Victor Ginsburg and collaborators, Ginsburg and Risch, and Ginsburg and Kajdan in general. For arbitrary groups, arbitrary reductive groups, you have that this guy here is finitely generated. So we can now just define the universal implosion as we define this guy to be a spec of this ring of invariance. But as part of that, in particular of the approach of Ginsburg and collaborators, something really interesting shows up. And so there's an extra feature. So this space right here has 2 copies of G acting on it, one multiplication on the left and the other on the right. when we're going to take our implosion, we're essentially using one of these. And as we said already on the real symplectic case, symplosion swaps an G action for an action of the maximal torus. So what you're expecting here is that on this universal implosion, you have the group times an extra copy of the maximal torus that is active. But actually, there's something more that was not showing up on the real symplectic or the algebraic side, which is that there's actually an extra action of the Weil group that is present. So we have a semi-direct product of the maximal torus and the Weil group. This group often is the normalizer of the maximal torus, but not always. But this guy always acts on my implosion. I'll just write it like so, T-G implosion. And so this is something really new. And this might seem very, very benign, but it's actually extremely interesting. Because whenever you're working with all of these spaces that I've mentioned so far, there's always sort of a shadow of the Weil group that is around. But here we actually have but typically you don't have an action. Here we actually have an action of the Weil group on the nose, and I'll say something more about that. So this is due to Ginzburg inversion. And so, and what was observed already by, another aspect that Dancer, Cronin, and Swan observed in type A, and that we have generalized now in arbitrary type, is that I mentioned that there's a very important toric variety around on the real symplectic or the algebraic side. What you have here is that there's a natural action of the hypertoric that sits inside of here. And it's the hypertoric that is exactly corresponding to the hyperplane arrangement that consists of the walls of the Weil chamber. So you actually have a Weil group action here, and that guy maps in. Now I'm already running out of time, so I'm not going to go into detail. But what this is actually giving you is a new perspective on the construction of the Springer representations. So people that are familiar with this, you have this Grothendieck-Springer resolution that has certain fibers, and on an open dense part of it, you have. So unfortunately, I don't have time to define this, but so this is only going to be intelligible for people already familiar with this. So if you take your Grothendieck-Springer resolution, there's a regular part in there that has an action of the Weil group, but the Weil group action doesn't extend to all of the Grothendieck-Springer resolution. However, this comes with a natural fibration, and you get representation of the Weil group on the cohomology of all of its fibers. In fact, you can recover all of the representations of the Weil group in this way. But it's a little bit weird because you have this sort of ghosts, this representation or this action of the Weil group on this cohomology that sort of pops up out of nowhere because it doesn't come from a geometric action. But what this tells you now is that there's actually another way of looking at it, which is to say that rather than just looking at the Grothendieck-Springer resolution, you have to look at a space that is even a little bit bigger. Namely, you take this implosion space, and now you quotient this as a stack by the maximal quotient. So this is a stack that naturally contains the Grothendieck-Springer resolution, and here the Weil group is acting. And so this hasn't really been worked out, but it allows you to construct, or at least the existence of the Springer representations becomes much clearer. Because now all of a sudden you just work stacked theoretically with this space, and there the Weil group is just manifestly present all the time. Okay, but I should move on if I want to say anything about contraction. So the final example of this pattern that I want to discuss is the case of contraction. Contraction is closely related to implosion in the following sense. This was 4. I think I'm now actually to 5, so this is contraction. So on the complex algebraic side, contraction was first introduced by Popov about 30 years ago. And what Popov did was as follows, and I'll just do it for the universal case. So you look at your group G, and you look at the ring of regular functions on G. This has a decomposition that through the Peter-Weyl theorem is very well understood, but we can make that into a filtration. We can put a filtration on this ring by choosing a dominant weight, a regular dominant weight, and so then this guy becomes filtered. Where the piece corresponding, it's filtered by the natural numbers. The piece corresponding to this is just the direct sum of those isotypical components that together, that pair with my regular weight to something less than n. And so whenever I have a filtration on my ring, I, of course, can switch to the associated graded. And in fact, when I look at the associated varieties, I get a one-parameter family that degenerates to this. So I have, that is what is known as the Riesz construction. So I get a GM equivariant family over the complex numbers, where the generic point, maybe the point over 1, is given by my group, and then I get a over 0. I get something else, which is known as the asymptotic semigroup of G. So that is a degeneration of my group. It's no longer a group, but it still has a semigroup operation that I get in this way. And so when we now want to think about the real symplectic version of this, so this was done jointly with Hilgert and Manon. There is a general procedure that is due to Harada and Cave that says that whenever you have one of these GM equivariant flat families over C, you can actually write down a vector field. This is an algebraic construction here, but I want to translate into something that is symplectic. So what we can write down is we can write down something known as the gradient Hamiltonian vector field, which it's both a gradient and a Hamiltonian vector field. So I have to choose a suitable Kähler structure on this. And then there's a very explicit recipe for this. I take the real part of this vibration. I take the gradient of that function, normalize it in a suitable way, and then I look at the flow of this. Now, this flow is going to be defined on the smooth part, but what Harada and Cave said is that in finite time it extends, so the flow of this extends to a map from G, or it works much more generally whenever you have this situation from the fiber over 1 to the fiber over 0 that is continuous, surjective, and generically a symplectomorphism. So they showed these existence results that you have whenever you have one of these test configurations, if you want, I think for people coming from K-stability, that you get this way. But in general, how this map looks is very hard to make explicit. But what you can now do in the case of, in this contraction case, when you're focusing on this story that comes out of the contraction of Popov, this flat family here actually has a monoid operation. So we have a monoid structure here. This guy sits inside of the group of units of this monoid. And this asymptotic semigroup is also part of the monoid structure. We have a lot of extra information available that actually allows us to completely make this chase down what the flow of this vector field does.
Is it the same as taking points on a giant fiber?
I mean, do you get a map down to that this way? So I don't know actually. The only way that I get I mean, the map is in general is not an algebraic. It's just a symplectic morphism. Yeah. So algebraically, you just have a degeneration, but on the symplectic side, and this is another example of sort of having to look at the same phenomenon really in two different ways, you get this this symplectic morphism. And so what it now becomes is something.
Generates to a singular curve of P1 degenerates to a nodal curve, and then the map should divide the northern and southern hemispheres. Somehow we normalize it. It is a kind of limit.
So what you find now here on the real side is that the flow that you get in this way is just a map that sends x to x quotiented out by exactly the same equivalence relation that we already saw on the contraction side. Now, when you were doing the contraction, we were taking a pre-image of this positive Weil chamber and then putting this funny equivalence relation on here. Now we're doing that to all of our space. So this equivalence relation can be defined everywhere. And so that's what we're doing. So you look at the stabilizers of your momenta, and what you're doing is where the momenta are not regular, you're just crimping these commutator subgroups. And so a basic example, maybe that's the one I should write down. Is the case for G is equal to SL2, in which case we have that this total space is nothing but the space of 2 by 2 matrices, where the map down to C is our determinant. And we can identify SL2 with the cotangent bundle of SU2. And so what you're doing here now is you map this down to the imploded space, which symplectically is just this cotangent bundle where you collapse the zero section. And algebraically, this is just a cone over the quadric that corresponds, of course, to the zero fiber of the determinant map, which is the 2 by 2 singular matrices. Okay, I'm almost out of time, so I just want to now get to the most recent part, which is the case of the holomorphic or the complex symplectic contraction. So maybe I can just say that the prime example of this contracting operation is given by the Gelfand-Zeppelin story. So Gelfand-Zetlin provides you a toric degeneration of the flag variety, at least in type A, which is obtained by an iteration of this procedure. So that is sort of the main example to keep in mind, the toric degeneration of the type A flag variety. And so now the complex symplectic version, the contraction, so this asymptotic semigroup of G, can itself also be understood as two copies of the implosion. So this is just in the algebraic setting. I implode on the left, I implode on the right, I take these two copies, and now I reduce by a maximal torus. So if you just do a quick dimension check, you see that whenever you take this procedure, I'm back at the dimension of the group, and that's indeed what I get. And so what you can now do, on the holomorphic symplectic side is you can actually take this as a definition. So you take two copies of the complex symplectic implosion. And you reduce this by, in the hyperkahler sense now, by the complex torus. And so this has now is a space that on the algebraic side has a lot of the same similarities, or on the algebraic symplectic side has a lot of the same similarities. And in particular, now it's going to have an action of this guy is going to have an action of two copies of the group, and then the same extra copy of the wild group that shows up. I'm almost out of time, or I am already out of time. So let me just see if I can say anything more here. So there's still many aspects of this holomorphic symplectic implosion contraction that we don't quite understand, but all of these operations that I've mentioned so far, the holomorphic symplectic story always combines ingredients from the algebraic and from the real symplectic picture. How exactly that happens here is a little bit unclear. But what we do know is that you don't quite have a map down to the contraction. Sorry, I should say this is the contraction now. We don't quite have a map of the original space. Or maybe I'll say it in general. We would like to have, again, a map like so, but that's not quite what we get here. Rather, what we get here is that you have to slightly twist this space, which is just by replacing it by the semi-direct product of the Grothendieck-Springer resolution and the original space using the moment map. So you have to modify that. That is to say, for every moment, complex moment, you actually have to add a choice of a flag. Once you do that, you do get this map to the contraction. That again, now it's going to be generically finite and a Poisson map. So yeah, there's some more things I want to say, but I'm already over time, so I'll stop here.
May I try to summarize the main theme of what you said? And I don't know if this is correct or not. So tell me if this is to be considered correct. If you study the category of G spaces in algebraic or symplectic geometry, one way, given one G space X, and you can produce another one, is simply to take the quotient and then the trivial at Vx. But there are other things you could do, such as to blow up G orbits or to compactify in some way. And those other constructions, I think that philosophy should be regarded as taking some canonical G space, causing it with X and then taking the quotient of the product.
Yeah.
And so once you realize that the case, what you do is go out and look for more or less canonical G spaces, and you could use it this auxiliary space. And for each one of them, you say, well, what type of enlargement operation do I get on category?
That's essentially true. So you can even formalize that, and that's something that ties in with something known as Moore-Tachikawa theory. So there's a category whose objects are reductive groups and whose morphisms are spaces. So if you have a morphism from a group G1 to G2, it's just a space with a G1 times G2 action. And composition in this category is exactly given by taking products and reducing by the diagonal action of the middle group. And so what you're saying, and that's definitely essentially the theme, is that all of these spaces, and essentially any space that is sort of relevant in basic geometric representation theory, if you sort of run through the list of spaces that I wrote down as universal ones, pretty much everyone shows up in that list. So all of these things are preferred morphisms in the Moore-Tachikawa category. So that's just an organizational way of thinking about that.
Could you say just a little bit more about this example of 2x2 matrices? So,
yeah. So
what is the GM action?
So the GM action is just given by so you just multiply by diagonal multiples of the identity. You just scale multiplication. Yeah, that's it.
Okay, so then the specialization under the GM action is just the matrix with the diagonal entry 0.
Yes, but that's not.
That's different.
That's definitely different.
So what is?
So you have a map here that so the easiest way to understand this is in terms of Lie group decomposition. So if you think about the generic part of here as just GL2, you use the KAK decomposition, where K is just SLN and A is the maximal torus of GL2R. And this flow map is completely equivariant. So what it tells you is that you just need to understand what happens on the A part. And so when you have now a real number X and you get the associated diagonal matrix here. So what this you just push. I mean, this becomes extremely explicit. You just write down the vector field and you flow it. And so what this goes to is the square roots of x squared minus x to the minus 2, 0, 0, 0, if x is greater than 1, and the lower version of it, x to the minus 2 minus x squared, if x is less than 1. So it's an extremely explicit map. So in general, this gradient Hamiltonian vector field, you can't really do anything with it, but because you have these Lie group decompositions available, you can completely push it forward. So this is what it looks like for SL2. You can actually do that for arbitrary groups, and then it's just a matter of verifying what happens to the stabilizers of these endpoints. And there you see exactly that equivalence relation showing up. Did I write it down? This the one up there. That shows up as the stabilizers of these endpoints.
Why is this all flat? Is that the determinant not from 2x2 matrices to C?
Yes.
But obvious.
That is flat? Yeah, good question. It is. Yes, it's SL. General fiber is SL. And then the specific, fiber is the 2x2 singular matrices. So this definitely, I mean, this is just a special case of a general theory developed by Edinburgh, and the flatness is he establishes that in great generality. So.
Any other questions? Okay, thank you.